Hey everyone, this section is about actually doing some integration in polar coordinates. And so this is a full day's worth of a lecture, so this video will probably end up being kind of long. I think that you can change the speed at which you watch it, but more details on that later. Okay, so we saw in 10.3 that the area within a polar region between angles alpha and beta is 1/2 f of theta quantity squared d theta, where f of theta is usually described by an equation in terms of theta where r is set equal to that equation or that expression. Okay, so then what is our r? Well, r would be sine 3 theta squared, because in the integral it's raised to the 4th power. So I'm not going to graph all of these as we go through this worksheet, but just as a refresher, the way you can figure out what a polar curve looks like is just by plotting some points. So let's look at a couple values for theta. Obviously, we only care about theta between 0 and pi over 3, so let's just do some values within that range. So when theta is 0, our radius is sine squared of 3 times 0, which is just 0. When theta is pi over 6, we're looking at sine squared of 3 times pi over 6, which is sine squared of pi over 2. And so that's 1 squared, which is 1. If we look at pi over 3, then we're looking at sine squared of 3 times pi over 3, which is sine squared of pi, which is 0 times 0. So that's 0. And we could keep plotting just so we have an idea of what this thing looks like. Pi over 2, you're going to be looking at sine squared of 3 pi over 2, which is -1, but we're squaring it, so we get a +1. So in general, this is going to be what's called like a flower or a rose with 6 petals. So at every pi over 6, I guess they're spaced pi over 3 apart actually, you're going to have a petal that goes out and hits r equals 1 at its furthest point away. So this is the full polar graph of that polar equation. But what we want to compute is only the area of that polar curve between 0 and pi over 3. So just this piece. Okay. So that is the only part that integral represents. And we're not actually asked to compute that, but that yellow region is what we would be computing the area of. Okay, so the next problem, we are going to find the area enclosed by this canonical spiral. So if you think about y equals x being like the canonical equation in Cartesian coordinates, r equals theta ends up looking kind of weird. It looks like a spiral if you plot some points. So let's first just sketch that. And again, you can make a table of theta and r like we did in problem 1 to plot some points, but this is roughly speaking what that curve is going to look like. And it keeps going, but I'm only graphing the part of it that lives between 0 and 3 pi over 2 for theta. Okay, so we're finding the area enclosed by that spiral. So that's going to be this yellow region. Okay, so if we set this up, we know that the area is integral between our two values for theta, so 0 to 3 pi over 2, 1/2, whatever our function of theta is, quantity squared d theta. So we're looking at integrating from 0 to 3 pi over 2, 1/2 theta squared, because f of theta and r are the same, so we're just looking at the function that is theta, d theta. Okay, so that's not too bad since you're integrating with respect to theta. You're going to end up getting 1/2 times 1/3 theta cubed evaluated from theta equals 0 to theta equals 3 pi over 2. I guess you can plug that in, maybe. So 1/6 3 pi over 2 cubed. And that is the area of that yellow region. Okay, then we're asked to find the slope dy dx of the spiral at theta equals pi over 2. So when theta is pi over 2, that's right here on our polar curve. And so that curve, of course, has a tangent line at that point, maybe something like that. And so we should be able to find the slope of that, which we're calling dy dx. Okay. All right, so to do this, we're actually going to write, since we're finding dy dx, we know that we want to start with an equation involving y and x. So we're going to replace our polar equation, r equals theta, with a Cartesian equation. And that corresponding Cartesian equation would be, well, r is square root of x squared plus y squared. And theta, you have a lot of different expressions for theta in terms of inverse trigonometric functions. Let's just use arctan of y over x. Okay, so we have an equation involving x and y, and then what we need to do is implicitly differentiate with respect to x, both sides of this equation, and then solve for dy dx. So implicitly differentiating both sides, I'll just show you this first step, and then you guys know that a bunch of algebra is involved to actually solve for dy dx. So I might skip that, but the solutions will be on Canvas. So on the left-hand side, we have 1/2 x squared plus y squared, drop the power, and then apply the chain rule, but of course we're chaining with respect to x. So we get 2x plus 2y dy dx. And that is equal to derivative of arctan is 1 over 1 plus the argument, which is y over x, quantity squared, times the derivative of the inside, which is y over x, with respect to x. So we're going to have to do a little quotient rule. So the bottom times the derivative of the top minus the top times the derivative of the bottom all over the bottom squared. So that is the derivative of y over x with respect to x. So now you have an equation involving dy dx, and you'll have to get that obviously on the same side and combine it so that you can solve for it. In the end, what we're really looking for is dy dx when our polar coordinates, theta, let's do r theta. When our polar coordinates are theta, which at pi over 2 would be pi over 2, pi over 2, we'd be looking at when that, what dy dx is at that polar coordinate. But our dy dx, of course, will not have r's and thetas. It will have x's and y's. So this will really be, well, what is x at this point? It's 0. And what is the y value at this point? Well, it's actually the radial length, pi over 2. Okay, so this ends up being, after you simplify a whole bunch, minus 2 over pi. And from the look of our tangent line, it looks like it has a negative slope, and it doesn't look that steep. So that seems like a reasonable number. Okay, great. So a common question in calculus with polar coordinates is finding the area not just within a single curve, but between two curves. So inside of one curve and outside of another. And if you remember, we could find the area between two curves given in Cartesian coordinates essentially by taking their difference and integrating the difference of the two functions f of x minus g of x. So that's basically what we're going to do here, but we have to think about what the difference looks like. So here we've got the curve r equals theta, which is the same curve we had above. But then we have a second curve, r equals 3 theta. And we need to be careful that we always know which curve is on the outside over a given length for theta. So I'm going to copy our picture up here actually. Okay. And get rid of all that. Cool. Okay, so there is our curve r equals theta. So r equals 3 theta is basically just going to have the same shape, but it's going to get bigger a lot faster. Okay, because it's taking whatever angle you're at, theta, and it is scaling it by 3 instead of being equal to theta. Okay, so the polar area the polar region we are trying to compute the area of is the area that is within these two polar curves. So it would be this region. All right, so the same logic applies as in the Cartesian setting. I think it's like section 5.1, area between curves. So the smaller area, well, let's start with the larger area. The larger area is going to be given by the integral from 0 to 3 pi over 2, 1/2. What is the equation for our larger curve? It's 3 theta, and then we need to square that and integrate with respect to theta. But then we need to subtract off this region that we're not hitting. Okay, and that region is the integral from 0 to 3 pi over 2, 1/2. Our function there is theta squared d theta. Okay, so what we're really looking at when we combine these two integrals that have the same theta values, we're looking at the integral from 0 to 3 pi over 2, 1/2 3 theta squared minus theta squared d theta. Okay, so integrating with respect to theta, you use the reverse power rule. There's really no tricks here. So I'm just going to put ... equals, the final answer should be 3 pi over 2 cubed all over 3. Okay, so you can check the solution, the steps here on the full solution sheet on Canvas. Okay, so problem 4 is very, very similar, except we're looking at a curve, a family of curves that we haven't talked about yet. They're called cardioids. These end up looking, and again, all you have to do is plot some theta and r values to get an idea of what this looks like. But this particular cardioid ends up kind of looking like a pumpkin, like that. It should be symmetric with respect to the x-axis, but forgive me. Okay, so what we're really looking at, because we're looking at the area where theta ranges between 0 and 2 pi, is the entire yellow region I just highlighted. So setting up your integral, your limits would be from 0 to 2 pi, 1/2. Your curve, r is 1 minus cosine theta, so you would be taking the expression for r, squaring that expression, d theta. And again, there's some steps here, but you end up using a half angle formula because you end up getting a cosine squared in your integrand. So you can see the full steps there for how this final answer comes about. But the setup is what's important, and then beyond that, there's a trigonometric identity that you have to use. But I think you guys can follow along on the solutions. Okay, here's another rose. So we've got the 4 petal rose, r equals 3 sine of 2 theta. So what that guy is going to look like, again, you can create a table of values with thetas and r's and plot some points. But this thing is going to have 4 petals, all at an angle of pi over 4. And at those angles, so this is pi over 4. Oops, we always graph r first. So r, when theta is pi over 4, puts out a 3. So 3 at all of these all of these angles. So this is 3, 5 pi over 4 and 3, 7 pi over 4. Okay, and they just want us to find the area of one petal, so just one of these guys. So we can simply integrate but just within the first quadrant. So when we set this up, make sure that you note that the first angle that we're given is all the way down here at 0. So we need to start at 0, and we keep integrating until pi over 2. So those are our bounds for theta. Then we're going to have 1/2 the expression for r, which is 3 sine of 2 theta, square that expression, d theta. Okay, so another half angle formula comes up in this computation. You can follow along with that in the solutions. The final answer is 9 pi over 2. Okay, the second part of this question says, oops, well, there's a little pentagon around your final answer. Okay, then find the length of the curve that makes one petal of that same rose. So we're simply computing the length of this blue curve. Okay, and that was also derived in in section 10.3. So let me label this. So this is the area, but then the arc length, if you'll remember, the arc length in polar coordinates, you still have your angle bounds from alpha to beta depending on the region you're looking at. Our region will be 0 to pi over 2. And then the expression you integrate is r d theta, because that's exactly what arc length is. Arc length is the radius times the change in theta. Okay, great. So for us, we're still integrating from 0 to pi over 2. Those are the angles through which the blue curve is given. And then r is 3 sine 2 theta d theta. Okay, so there's no real tricks here. You need to do maybe a substitution because you've got 2 theta instead of just theta inside of sine. But what this comes out to, again, you can look at the solutions if you need to. This ends up being 3. So this thing has a total area of, a total arc length for that one petal of 3. Okay. Moving right along. Back to something similar up here to problem 3. We want to find the area outside a particular polar region, but inside another polar region. So r equals 3 is just a circle that's saying graph all of the points that are exactly a distance of 3 from the origin. But inside the cardioid, r equals 2 plus 2 sine theta. So the circle that we're looking at, let's sketch that. Okay. Nope. Okay. So we got a circle. Its radius is 3. And then we've got this cardioid. You can plot points for this cardioid if you want to, and you probably should just for the practice. But this cardioid ends up, again, kind of looking like a weird little pumpkin, and it does something like that. Okay, again, it should be symmetric on this side, so let me try to make that look a little bit nicer. Okay. So we want to find the area of the region between these two curves. So outside the red curve, but inside the blue. So that's just this little sliver in yellow that I just highlighted. And I got colored outside the lines. So within the red and the blue. All right. So what becomes more challenging about this problem compared to problem 3 is in problem 3, the bounds for theta were very obvious, 0 to 3 pi over 2. But in this problem, we're actually going to have to work to find the places where these intersect. So as a matter of fact, I'm going to redraw that curve because it's not actually where it's supposed to be. Okay, so we're still finding this yellow region here, but the places where these curves intersect, which would be right here and right here, those are what we need to find. So the radial, not the radial, the angles that those 2 points are at are what we need to find. Okay, so part B is asking exactly for that. So we are wondering where the curve 2 plus 2 sine theta, what value of theta makes the radius of that expression equal to the radius of the other expression. Well, this equation is valid if and only if this equation is valid, if and only if this equation is valid. And then we have to ask ourselves, okay, so what values of theta make sine of theta equal to 1/2? And you're more than welcome to take arcsine of 1/2, but just remember that your calculator, when you do this, is only going to give you one value when really it's clear that there are 2 different values. So your calculator is only going to give you theta equals pi over 6, but you can see that that's only your alpha. So you'll have to, if you use a calculator, you'll have to know that there's another angle that's a reflection across the y-axis of, what would that be? 5 pi over 6. Okay, so pi over 6 and 5 pi over 6 are the 2 angles where these curves intersect, and we need both. Okay, now that we have this, we can use the exact same logic as what we did in problem 3. We can say, well, the outer curve on that region is going to be have an area that is represented by the integral pi over 6 to 5 pi over 6, 1/2 2 plus 2 sine theta, that expression for r squared, d theta, and then we need to subtract off the inner curve, which is given by pi over 6 to 5 pi over 6, 1/2 expression for r, which is simply 3 d theta. Okay, so finally, this has another half angle that comes up. So there's a trig identity that happens. Oh, I can't spell identity. I wasn't looking at what I was doing. Don't judge me. Okay, so there's another half angle formula that comes up. You can see the solutions on Canvas, but this ends up simplifying to 9 root 3 over 2 minus pi. And by the way, one way to make sure, just a simple check that your answer is not totally unreasonable, we're computing an area. So if you did it right, you should get a number that's larger than 0. And 9 root 3 over 2 minus pi is a positive number. So that's just a quick check that you didn't do something totally wrong. Okay, last page, everyone. So problem 7 is very similar to problem 6, but something kind of weird happens with this problem. So part of me wants to skip to part C just so you can see what goes wrong if we're not careful. So if all we do is we say, well, where are these two curves intersect? So we'd be saying, when is 2 cosine theta equal to 1 plus 1 cosine theta? We're going to get that if we subtract a cosine theta over, we get cosine theta equals a positive 1, and that only happens at theta equals 0 or, 2 pi times an integer. So then, does that mean that we should be integrating from 0 to 2 pi of the larger curve, which will be 1 plus cosine theta squared minus our smaller curve, which is 2 cosine theta squared. Okay, so here's the issue, and we're going to go back and explore this in part A. But this curve, if we look at this curve between 0 and 2 pi, it will actually have traced itself twice. And we don't want to go around that curve twice. We only want to go around it once. And so this is kind of a subtle thing, but there is purpose in sketching your polar region and understanding what values of theta result in the curve tracing itself once, twice. So let's go back up here. So if we look at the polar curve r equals 2 cosine of theta, if we start at 0, cosine of 0 is 1, so that's 2. If we look at pi over 4, well, 2 cosine of pi over 4, cosine of pi over 4 is root 2 over 2, right? So we'll get a root 2. Okay. Pi over 2, cosine of pi over 2 is 0. Let's look at 3 pi over 4. So we'll have 2 cosine of 3 pi over 4. Well, that's just a reflection across the y-axis. So we get a negative root 2. And then at pi, this is kind of weird. At pi, we get 2 cosine of pi, which is 2 times negative 1, which is a negative 2. And remember that when you're graphing negative values for the radius, that requires you to reflect across the origin. So here's what I mean by that. Let's plot some of these points. Okay, so our first point is theta is 0 and r is 2. So let's do that point. That's when theta is 0 and r is 2. These are all in polar, by the way, so be careful. Okay, so that's a polar coordinate. And then we've got pi over 4. Theta is, not theta, r is a positive root 2. Okay, then we have pi over 2, so that would be this angle, with r equals 0. Okay, so 0 pi over 2. And then we get into these two coordinates. 3 pi over 4, which should really be, oops, not down there. 3 pi over 4 is over here, but we're graphing the radius negative root 2. So we're actually going to have to flip that negative root 2 to be down here. Okay, and then at pi, which should technically be over here, we would be graphing negative 2. Well, that would require us to flip it over here, and now we're back on top of 2, 0. So this is both negative 2 pi and 2, 0. Okay, so it turns out that 2 cosine theta, r equals 2 cosine theta, actually only requires pi, 0 to pi, to trace its entire curve. So it starts there at 0, comes up here to pi over 4, comes to here at pi over 2, but then at 3 pi over 4 ends up down here, and at pi it ends up back where it started. So it does trace a circle, but it only takes pi to do it. Okay, so then if we're going to sketch the region that we're actually finding the area of, that's the region that is outside the curve in part A, but inside the curve 1 plus cosine theta, which, by the way, is another cardioid, another little pumpkin. So let me draw our inner curve, okay? But then our outer curve does something like this. Okay, So we are finding this yellow shaded region, the area of this yellow shaded region. But again, we have to be super careful because this cardioid actually requires theta to range between 0 and 2 pi to complete its entire rotation, whereas the red curve ends its rotation at pi. So how are we supposed to set up an integral that doesn't retrace our area from 0 to pi? Okay, so let's just think about this. Given that the red curve is just a circle and it lies completely inside of the cardioid 1 plus cosine theta, why don't we just subtract the area of this red circle that has radius 1? Does that sound reasonable? Okay, so then we would simply be finding the area of the blue cardioid, the area inside the blue cardioid that needs to go from 0 to 2 pi to complete its entire rotation. 1/2 1 plus cosine theta quantity squared d theta, and then we'll be subtracting the area of a circle of radius 1 since the entire thing lies inside of that cardioid. Great. Okay, so this ends up being, again, some steps here, but this ends up being pi plus pi over 2. And of course, the area of a circle of radius 1 is pi times 1 squared, so we'd be subtracting pi. So the resulting area that lies between the red and blue curves is just pi over 2. Okay, so some examples of finding area inside a curve, between two curves, and being super careful in problems 6 and 7 to find where the curves intersect, and also understanding how long it takes a curve to trace its entire shape. All right, thanks for listening.